So my name is Kevin Crawley. I am from Nashville, Tennessee in the United States. And I work for a company called Instana, which is a application performance management tooling company. I also work for a startup in Nashville that I helped co-found called Single Music. And I'll talk a little bit more about what we do at those two companies later in the presentation. But first, we'll talk a little bit about how game theory can help us change our organization and some of the behaviors as we move towards more agile and DevOps practices. So just a little bit about me before we get started on the topic of discussion today. I am a Docker captain, which just means that Docker has recognized my contributions to the community through my local meetup group and through the DockerCon conference series. I'm also a GitLab Hero, which is a source control management tool, GitLab, and they've recognized also some of my community contributions and some of the work I've done to evangelize and promote GitLab as a tool and a solution. I've organized DevOps Days Nashville coming up on 2 years now, and I've been doing software development of some sort for about 20 years, where I've been doing DevOps and SRE types practices for almost 6 years now. So some of the things we're going to talk about today is how we can leverage game theory to tear down silos within our organization. And we're going to talk about the characteristics of the organizations that are high performing and what that means. Also, we're going to talk, and then we're going to move into how DevOps and site reliability engineers help organizations push past some of the barriers of initial automation within their organizations and how SREs need tools and what they require to be effective in their organization to manage large and distributed applications. So before we start talking about game theory, I do want to call out the fact that I'm terrible at math. It was literally the dreaded subject in school, but I'm going to try and explain some of the principles behind game theory without butchering it. If there's any mathematicians in the room, I apologize. So a lot of this material was actually inspired by Nirmal, who is also a Docker captain. And so if you're interested in learning more about game theory, I would suggest listening to some of his talks on YouTube. So the first thing I want to talk about is bad equilibrium, which is it's a strategy in game theory that says that all players can adopt and converge on this strategy, but it doesn't produce a desirable outcome for anyone. And to kind of illustrate this point, I'm taking a slide from the DORA State of DevOps report, which if any of you have not read that report, it's an amazing summary of how DevOps transforms organizations and helps them automate and bring positive changes to their IT infrastructure. So in the first stage, teams begin to transform, they start automating things, and they see really quick wins. This is like picking off the low-hanging fruit from a tree. And the automation will help those low performers kind of move into the medium performers, and we'll talk about the difference between low, medium, and high performers a little bit later. But once the low-hanging fruit has kind of been taken care of, all of a sudden we have an increase in test requirements, an increase in complexity, and all these things which were handled manually and traditionally and are very edge case-like are very hard to automate. And so all this technical debt suddenly rises to the surface, and these organizations have a real hard time pushing past this low end of the curve. Now, the idea here is that organizations need to push past that to get to the high-performing stage of DevOps and automation. And if they get past that, then they see incredible returns, hundreds of deployments per day. Changes take less than hours to implement and deploy, and overall, everybody's happier in the organization. There's less toil and pain when alerts are fired and less people are woken up at 2 o'clock in the morning. But the point is that bad equilibrium is this idea that we're going to focus on this automation and then stop because it gets hard. We have to move past that difficult stage. So, and the reason that this toil and this pain surfaces is because we have silos in our organizations. And we can define silos as points of contention in our organization where change management policy and requirements are high. The risk is really high, and we have all of this process around, well, to make a change, we have to do all these test cases, we have to have approvals from 5 different departments, and those types of business requirements are very difficult to automate. So, how many here have heard of the prisoner's dilemma, Nash equilibrium? Got a few hands. Okay, so this is a concept in game theory where the optimal outcome of the game is where no one player has an incentive to really deviate or change their strategy after considering their opponent's choice. And a good example of this is a game show that was in several years ago in the UK, and we'll watch the game show now and see what happens.
I know you're the last 2 people in the country I have to explain this to, but you have 2 final golden balls. You each have a golden ball with the word split written inside. You each have a golden ball with the word steal written inside. You will make a conscious choice of choosing the split or the steal ball. If you both choose the split ball, you split today's jackpot of £100,150 and you go home with £50,075. If one of you splits and one of you steals, whoever chooses the steal ball will go home with £100,150. And the person who chooses the split ball goes home with nothing. If you both choose the steal ball, you go home with nothing. Okay. I think you have some talking to do to each other.
Stephen, I just hope they weren't puppy dog tears and they were real tears and you were genuinely going to split that money.
I am going to split this. I just 50,000. I'm just, it's unbelievable. I'm very, very happy to go home with 50,000.
You were genuinely going to split.
If I stole off you, every single person there would run over here and lynch me.
There was no way I could. I mean, everyone who knew me would just be disgusted if I stole.
When people watch this, they're not going to believe it.
Please.
I can look you in the, Sarah, I can look you straight in the eye and tell you I am going to split. I swear down to you, I am going to split.
Okay. This is serious money.
It is.
Sarah, Steve, choose either the split or the steal ball now. Hold it up.
We're going on with 50 grand each. I promise you that.
Split or steal? You never know what's coming in this game.
All right, so as we can see here, Sarah had no problem with stealing the money. She is completely okay with everybody being disgusted with her. Now, what happens here is in the Nash equilibrium, as I mentioned, the players don't really have any motivation or incentive to change their decision. Like once she had decided that she was going to steal, that was it. And the reason that the Nash equilibrium is such an interesting problem, especially when we start talking about how our organizations operate, is that a lot of times in our IT organizations, this is some of the default behaviors we see. Now, what happened was, as you can see here in the graph, both opponents, they're most motivated by getting all of the money. And the creators of the show, they are motivated for both of the opponents to be driven by this goal of taking all of the money, because in most cases both people choose steal and nobody gets anything, and the game show doesn't have to pay out any of the money. So in most cases, as I said, most people steal and the game show actually wins. So another example in game theory is something called Pareto efficiency, which there's Pareto efficiency and Pareto inefficiency. And Pareto efficiency is the idea of our resources are being allocated in a way in which it's impossible for any one individual to be better off without making at least one individual worse off. In other words, it's a zero-sum game. And we don't want zero-sum games in our organizations. We want people to be able to make trade-offs and be able to be empowered to develop and build tools and applications without people fighting and going after each other. Another way of saying what a zero-sum game is war games. Like, nobody wins if everybody starts lobbing nuclear weapons at each other. Now, Pareto inefficiency is the situation, it becomes inefficient if someone can be made better off, even after compensating those who made worse off. So if the idea here is that even though, say, the operations department has to go through all of this pain and effort, and they suffer for a while going through all of this change and automation work, the end goal is that the organization is going to be better because the developers are going to be able to ship software faster. We want Pareto inefficiency, but we don't want it combined with the Nash equilibrium, because that's a bad equilibrium, as I mentioned earlier in the slide. And a good example of how we can change that is here. And I'm going to apologize in advance. The audio in this is bad. I couldn't find a better source. So please bear with it.
Nick, Ibrahim.
Ibrahim, I want you to trust me. 100% I'm going to pick the steel ball.
Sorry, you're going to...
I'm going to choose the steel ball.
You're going to take
I
steel?
want you to do split, and I promise you that I will split the money with you.
Well, after you've took the steel?
Yeah.
You're going to take steel?
Yeah.
I'm going to take split?
Yeah.
So you take the money?
And I will split it with you.
After the show?
Yeah. Ibrahim, I promise you I'll do that. If you do steal, we both walk away with nothing. I'm telling you 100% I'm going to do it.
I appreciate that. Right, I'll give you another alternative. Why don't we just both pick split?
I'm not going to pick split. I'm going to steal. Ibrahim, honestly, 100% I'm going to steal.
It's in your nature to steal.
No, I'm honest, and I'm going to tell you...
You're an honest
I am. That's why I'm telling you I'm going to steal. If you do split, then I will split the money.
I can't see myself doing that.
Okay, well, I'm going to steal, so we're going to leave with nothing.
Where's your brains coming from? I can't work out...
I know that I'm a decent guy, and I will split the money with you.
Well, we should just both split then.
No, I'm going to do steal.
There is no legal requirement
there is
for him to give you the money.
Of course. So...
Ibrahim, I'm going to steal. So you've got the choice. You either steal, and we both walk away with nothing, because you know I've told you my intention, and I've told you that I will split the money with you, Ibrahim.
If I gave you my word that I was going to split, I would split. And you're going to take steal, so...
The only way you can guarantee to walk away with 6,800
is by sharing.
to guarantee that you both put the split ball in. And I do now have to push you for a decision. It's a tough one.
We've lost it. We've lost everything.
Okay, lost then.
We're walking away with no money because you're an idiot.
No, that's not
You're an idiot. You're an idiot. That's what you are. You're an idiot. You're an idiot. That's what you are.
This can go on all night, and these people have got to get up for breakfast. Nick, choose split or steal. Ibrahim, choose split or steal. Now, please. Choose a ball.
Right, I'll tell you what, I'm going to go with you.
Okay.
I'm going to go with
I promise you I will split it.
You cannot change your balls now. Split or steal. Yes, congratulations, you're both split and each received £6,800.
Why did you put me through that? Why did you do it to me? You're the worst person I've ever met.
That was a good one, wasn't it?
So, interestingly enough, after that episode, the show was canceled because they essentially broke the game. Everybody after that point declared their intention, and what most people did, and all of a sudden, the show had to start paying out nearly every episode. So the point here is that if you don't like the game, we can change it, right? And we did so by the Nash equilibrium. Isn't fixed. You can change it based on how you present yourself and how you solve problems in your organization. Now, in this case, Nick said to Ibrahim, "I'm going to steal it, and you have a choice. You can either split or you can steal, and none of us get anything." And so, as a result of that, Ibrahim analyzed the situation and he said, okay, well, it's risky, but it's better than nothing. So I'm just going to go ahead and go with split, and we'll see what happens. Right? So the new Nash equilibrium is that both people are splitting, and everybody walks away with something. And how we know this is because we apply the principles of Pareto inefficiency to the Nash equilibrium, and it gives us permission and gives us the proof that we can actually change the game. So how does this apply to IT, and how does it apply to software development? If developers and operations are both responsible for the operations of their applications, then all of a sudden we have a new paradigm, we have a new game. So just to get a quick poll from the audience, how many of you are software developers? All right, keep your hand up if you're on call. You should be on call, all of you. Like, the idea here is that if your application breaks in production, you should have to solve it along with the operations people. And that's the argument I'm trying to make here, is that in order for us to change the game and become more efficient, everybody has to work together. Now, I mentioned earlier that as organizations start transforming and they start building automation, we see a reduction in the amount of work being done manually, and we have certain categories of performers here. We have elite, high, and low performers. And this, again, comes from the DORA State of DevOps report, and this is from 2018. I need to update this for 2019, but what you can see here that the elite performers, they do very little manual work, whereas the low performers, they do quite a bit. And what are the characteristics of high and low performers? Well, you can see here that high performers and elite performers do deployments between 1 hour and 1 day. Elite performers tend to do several deployments a day. The lead time for changes, or how long does it take for a change to be proposed, as in committed as code, and the change pushed to production, less than a day, and between less than 1 day and 1 week. The mean time to recovery, or MTTR, is less than 1 day for high performers, and it's even lower for elite performers. It takes hours, sometimes minutes, to fix a problem in production. And the change failure rate is actually higher for low performers. Even though the low performers are delivering software at a much slower cadence, somewhere around once per week or per month, their change failure rate is much higher because they're not very good at deploying software. They're not very good at making sure that the changes they're making are small and isolated and compact. And as a result of that, the changes that they're making are big and they're prone to failure, whereas the changes that the high and elite performers are making are much smaller, so the chance of failure is much less. So as we tear down those silos, as we start working together as a team, DevOps organizations, they see new problems emerge. It's not like all the problems go away, it's just we switch to a new set of problems. And some of the problems that these organizations experience as they ship more software and more often is complexity tends to increase, and the reliability initially starts to decline. It's that J-curve we talked about. So as a result of that, we tend to focus our efforts less on the automation work, and we start to solve scalability and reliability issues. Alternatively, we just give up and we just go back to our monolith. Here's where site reliability engineers come in. And again, this is where we start moving out of that low end of the J-curve and up to the top. And some of the tools and the processes that organizations who have been successful at this have adopted is communication and collaboration tools, things like Slack or Teams, obviously using some sort of version control management, CI/CD, Pagerduty, OpsGenie, these tools that help collaboration and bring awareness to how our systems are operating in production. We also have an adoption of observability tooling. Now, I'm going to talk a little bit about observability from a high-level standpoint, like some of the problems observability solves in a technical organization. But there's some pretty good talks coming up later that I wish were in English so I could actually understand them. But I would highly recommend going to the Tracing for Java Developers by Philip Kren at 2 o'clock to learn a little bit more how distributed tracing works. I'm going to cover it briefly here in a moment, but probably not nearly as in depth as that talk. Also at 4:20 or 16:20, observability, the good, the bad, and the ugly. Again, probably another really good talk to learn about observability and how we monitor production applications. And then, of course, at 6:30, Need for Testers is a Lie. I really wish that one was in English because I have a similar talk where we talk about the idea of really, really good monitoring or observability can almost take the place of testing. At least that's what my talk is about. I'd be really interested in seeing that one as well. The last one I want to mention is Maxim Gorbachev. I probably butchered that name. The value of observability in production microservices tomorrow at 4:10. I'd also recommend seeing that one. So what do SREs care about? What do I care about? I care about reliability. That one's kind of obvious. Site reliability engineer, right? Performance. Is the customer happy? Are my users happy? And the customer can be an end user, or the customer could be my colleagues or my team, the business. And cost, is the business happy? Nobody likes spending a ton of money, so the idea here is that we're being frugal and efficient with our resources. So SREs are really in the business of measurement and defining objectives through service level objectives, and they do that by measuring SLIs, which is service level indicators. And SLIs is a term from the SRE handbook by Google, and they talk about what SREs want to measure. That includes things like, what's my error rate? What's the latency? What's the throughput and saturation? These are called the 4 golden signals, and again, you can read more about those in the Google handbook. So how do we get this data? How do we get the information from our system to tell us how latent processes are being, how latent are my endpoints, how many errors are being generated from a service or an application? And we talk about observability, but this idea actually originated a long time ago. In 1961, a gentleman by the name of Richard Coleman wrote a paper on the general theory of control systems. And what he said in this paper is that a system is observable if we can determine its behavior solely on looking at its inputs and outputs. And the lesson here is that we can take this approach instead of trying to reinvent it. So now, in terms of modern observability, this was first brought up by Twitter in 2016 when they wrote a blog post about the 4 pillars of observability. And they described it as we need monitoring, we need log aggregation and analytics, we need distributed systems tracing and the infrastructure to power that, and we need alerting and visualization, so we need dashboards. And I really like to think that we need more than just pillars. We need more than just those 4 things. We do need those 4 things, but we need that data to be contextual. We need those things to be interactive, and we need them connected so that when a log message is produced from our system, we can correlate it to a trace, or we can correlate it to some metric on that service so that we can understand if underlying infrastructure may be the cause of the problem, or if the application or program logic itself is the cause of the problem. And so Peter Bourgon wrote a blog in 2007 where he said that we need to bring these things together, right? We need to be able to have logging, tracing, and metrics. We combine all 3 of those, and then all of a sudden, we get request-scoped aggregatable events. And what this means is that it's not necessarily just about the tooling or the data. It's how we model and how we analyze that information. And it's somewhat similar to how DevOps is a mindset. Like, we have to be really proactive about collecting this data and analyzing it, because we don't want to treat our services like Schrodinger's cat. It's not a black box, right? And in order to do that, we need more context, more events around transaction, and we need advanced analysis tools to bring all of this information together so that we can understand it. And why does my organization need any of this, right? How many of us run staging environments? All right, how many of you actually trust it? I guess. Yeah, right? So, I mean, in reality, production is a zoo with thousands of monkeys trying to break things, right? Whereas staging is a little more sanitary. So another thing to look at is Uber's microservice graph. I mean, how do you reason about the performance of that application? That looks really complex, right? So in order to observe a system like that, we have to emit signals from it. We have to emit data about the inputs and the outputs, right? So when we aggregate that information, we can answer some really interesting questions like, how often are my services being requests are being executed against it? Are things being retried way too often? Are backoffs happening? We can also collect data around the request parameters. So things like query statements, the URL or URI, as well as things like where did this message go in the queue and what service picked it up and did the work after it went into the queue. We can also look at latency and outliers, things like P99s, percentiles. And we can also gather data around top-level exceptions, so things like stack traces, error logs, warning logs as well. And how does this data get collected? Well, it's distributed tracing, and it's also known as distributed structured logging. The idea of distributed tracing is that every request that happens in your system, every transaction between every service or message queue or database, data is collected around it, and context is retained. And context is retained by generating a header or metadata and injecting it into the request, and then extracting it when that request is picked up on the other side. Again, if you want to learn more about distributed tracing, I highly recommend going to the Tracing for Java Developers at 1400 hours, because he's going to go in depth with how it works. Also, we have to consider things like sampling versus no sampling, because as you can imagine, if we're collecting data around every single transaction in our system, it becomes heavy. It's a lot of information. So we have to decide whether or not we want to sample. If we do sample traces, then we may miss important outliers, things like P95s and P99s. So unless you're Uber or you're Twitter or somebody who has hundreds of millions of transactions an hour, you probably don't need to sample, so don't. If you do get into that area where the performance of your monitoring system starts to suffer, then obviously you want to incorporate sampling in some way. I'm not going to cover any of that. And if you want to learn more about it, Google is your friend. So how has observability helped DevOps culture? Well, I want to take a look at a production microservice application, actually Single Music, the startup. And I want to talk about some of the problems we've solved with distributed tracing at that organization. So Single Music, it's a very small team. We have a front-end engineer, a back-end engineer, and me, the principal SRE. I'm principal because I'm the only one, right? So we've seen quite a bit of growth. This chart is actually outdated. We have over 1,500 stores now. We integrate with Shopify directly, and we help artists sell their music. We distribute digital music and physical music. We do reporting to SoundScan and 7 Digital. These are the organizations which help songs and artists reach the Billboard Top 100. So Taylor Swift, Tool, 9 Inch Nails, stuff like that, right? We launched in 2018 with about 15 microservices. We're now over 35 microservices. We have over 20 integrations, about 200,000 lines of code now. We do over 20,000 transactions per hour, and we have less than 15% test coverage. And I'm proud of that, actually. And again, that's why I want to go to that talk. Need for testers is a lie, because I agree completely with that statement. Unfortunately, it's not in English, so I'll have to miss out. Now, we did build the deployment and the automation system for Single Music to be zero touch or one touch. And the idea here is that the developers on the team can define and build their own services without me having to do a thing. They create a Git repository, they throw some config files in there, the tooling automatically picks up on that service and deploys it for them. And then everything else is handled through the automation system. I literally have to do nothing for this company unless something catches on fire. It's great. So some of the bands that have picked up on Single Music and use us, and as you may have heard of some of these bands, we have even bigger names now at this point. Again, over 1,500 stores. So this is a somewhat large and complex application. Even though we have around 35 services, we run somewhere around 90 instances of application services in our infrastructure. This is because we do replication. We have multiple instances of each service for reliability purposes. So what you're looking at here, this is Instana. This is the company whom actually pays me. This tool allows us to visualize our infrastructure and get information and feedback about how it is running. So what you're looking at here is a 3D visual representation of our underlying infrastructure. So each individual stack is a host. And within each host, we're running many workloads. So this is a container system, so we can put a bunch of work on single host. And each individual layer in that stack is a service, and it's running inside of a Docker container. We can also visualize every transaction in our system between every service because of distributed tracing. Again, remember, we are tracking every single request between each service and the data around it. So we can get information around which service is talking to each other and also the performance of those individual requests. So things like how many requests are happening over a period of time, as well as what's our average latency and what's the error rate. Now, we can also analyze and build interactive dashboards for the distributed tracing aggregates. So what we're looking at here is a summary dashboard of every service in my application that's running in production. And there's multiple things happening in this dashboard, and what it tells me is at the very top, we have inbound calls, or how many requests are coming into my application over the last 12 hours, as well as what is my average error rate. So are any of these transactions failing? Am I getting a 500? Am I getting a 400? Is a database call coming back with an error, with a constraint problem? Is a message queue dropping my message? There could be any number of situations in which cause that error rate. But the point here is that I can easily figure out which endpoint and which service is creating that error by using the bottom two widgets, which bring up the most latent or the most erroneous endpoints or services in my system so that I can investigate and dig into those transactions which caused those errors. Another way to put this is that every single service in my application, I'm collecting those traces and creating an overview of each one of those services so that I can see information around what technology is being utilized within that service, as well as, again, what is my throughput, what's my incoming call rate, what is my latency, and what is my error rate. And it's really easy for me to click into any one of these and dig further and investigate problems as I see them in this dashboard. So what kind of problems have we solved using distributed tracing? We're able to visualize certain patterns and algorithms in our software. So can anybody recognize the back-off pattern here as we're trying to get a lock from a database? Just call it out if you know it. So this is what it's called an exponential back-off, and this is just being a good neighbor, right? So before we implemented this, we recognized that as a process was trying to obtain a lock, or in other words, it's trying to win a race, we would inevitably call our Redis database over 100,000 times within 30 seconds trying to grab this lock. So what we did is we implemented something that's called exponential backoff. And the idea is that we try to get the lock, and then if it fails, we try again. If it fails, we wait n number of seconds, try again. If it fails, wait n number of seconds plus 1, try again, n plus 3, n plus 5, n plus 10. And so that way, when a system comes back online or it inevitably fails, we haven't hammered a database or some sort of system of record trying to do this work. And you can see on the right-hand side, we get details around that transaction. We get information around what the stack trace is and also what the parameters and any sort of messaging that occurred. We can also recognize patterns in our databases, and we can see that a service is slowly dying here. We go from roughly 15, 20 milliseconds to over 2 seconds of waiting for a database to call to return information, even though our throughput is going down. So what we're seeing here is the system is gradually actually losing performance. And this is a problem, right? We don't want this to continue happening. Otherwise, everything's going to start timing out and failing. So what we found out is that we had a hibernate query causing an O n log n rise in latency. And the reason that this was happening is this was actually the first time that we processed around 40,000 sales in 6 hours. This is one of our biggest sales early when we first started the company. And every transaction that occurred in our system, we would load all the other transactions that had occurred before saving the new one. So as a result of that, it was a bad time for everybody. And with the observability tools, the fact that we were observing the performance of the database from the aspect of the application, we were able to deploy the fix and observe it immediately, as you can see here. Once we deployed it, we can see that the issue was resolved. We also are able to recognize patterns where the system is blocking requests, and this is an asynchronous transaction. When the transaction is blocked, no other work can occur. And so as a result of these calls here, we implemented a solution with Redis for caching that token However, we didn't account for the token policy changing. Auth0 sent us an email, we ignored it, and then all of a sudden it broke, right? Because after 30 seconds, the token expired. And again, observability tooling helps us visualize and see that problem because we know that this particular endpoint, we know that whenever the application is being installed, that it is failing because we can see down here on the right at around 32 seconds, 30 seconds, all of a sudden we have a bunch of failures, transactions happening against an external call. And we get the details around the error. We know that the token is invalid, and we know how to fix it now because we know exactly where the problem is happening. So once we fixed it, we can see that the transaction executes and completes perfectly fine. So that was great. The other thing that is really powerful about distributed tracing is that when we collect information about all these individual, very, very granular points of information, things like database queries, we can say, okay, well, we know that this database query is really slow. It's taking almost 300 milliseconds. Maybe we should put an index on it. So once we put an index on it, we can see that the performance improves drastically. We can see a reduction of the latency from 300 to almost 0 milliseconds. The other thing that's really important is context, right? So again, we're analyzing distributed systems where a lot of transactions happen in a short amount of time, and we have to retain context of them. You can see here on the left side that we have a small batch of transactions, and then it kind of waterfalls down. That's an asynchronous transaction. That is a message going onto a queue, and then a bunch of other work occurs. And something failed. We can see here on the top it says, well, there's an error, there's a warning, let's investigate it. If I click on that little red exclamation point, I'm taken to the actual problem that is happening, and I can investigate and really dig into where the problem is happening and hopefully fix it. In this case, we just had a duplicate job happen or a task, and it tried to insert a record and failed because that work had already been done. And again, it's really important to have context from a logging standpoint so that I can investigate from the logging side into the trace. So if I click on one of those logs, I get taken directly to the trace where that log was generated. The other thing that's really important is that we need to be able to build our own custom dashboards. And we utilize a mix of Instana, logs.io, and Grafana to manage our system. And I'm able to create Grafana custom dashboards based on all of this data that Instana collects so that I have a single view of the overall health of my system from an infrastructure standpoint so I can get information that I care about. And other people can get information they care about. They don't necessarily have to dive through 20 dashboards to get the information they need. Again, here's a dashboard where I am just pulling information using the Grafana Instana plugin from our application and getting information around the database, the message queues, and some of the more important endpoints in our system. So on top of changing the game in your organization and pushing towards automation and bringing everybody together to work on the same team, we also have to focus on observability because it enables the organization to understand the behavior of the system. It also empowers the engineers to find and fix problems. It enables us to build more reliable systems and ship software faster because we're more confident in that software. And we can also promote empathy through understanding, transparency, and communication. If everybody understands the problem, then we're not spending our time trying to explain it. So if you want to learn more about monitoring production microservice applications, you can follow me on Twitter. I do workshops on open tracing, soon to be open telemetry, and observability. And if you want to give Instana a spin, we have a 14-day free trial. Feel free to check it out. And please follow me. If you're on Twitter, not sure if Kevin, that's where I get every bit of my self-worth. So please follow me. Thank you very much.